Okay, here is the introduction to section 2.2. So what we're going to do in section 2.2 is we're just going to formalize this idea of derivative and generalize it from section 2.1. So here we have a fact. We can generalize the derivative of f of x with respect to x if the limit exists. Then f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So let's start by drawing a picture to illustrate this definition. Okay, let's say we have some function. Here is some function f of x. Let's say this is some point right here. Let me get a different color. Let me call this point just some general point on the x-axis. And then here is a point h units away on the x-axis. Okay, and I'm going to do my best to draw in the secant line between those 2 points. Okay, here is the point then on the curve. It has x coordinate x plus h. It has y coordinate, whatever the output of the function is at x plus h. And this has x coordinate x and y coordinate, whatever the output of the function is at x. Okay, then we come back up to this definition. What is going on? First, we're looking at this quotient right here, f of x plus h minus f of x. That looks like a change in y, divided by x plus h minus x, which is just h. So this is the slope of that secant line. Okay, and then what do? We let h go to 0. So h goes to 0, moves this point in this direction. It's going to move this point along the curve, and eventually, if we let h go to 0, that would give us the slope of this line, which is the tangent line. So when we take these pieces together, we get slope of the tangent line. And we're going to get it as a function, f prime of x. So basically it's going to take an input, x, some number, and its output is going to be the slope of the tangent line to our original curve, f of x. Okay, I'm going to rely on this definition of the derivative probably the rest of the quarter, but just in case you see this other version in the text, I want to at least write it down here. So we could rename this point. This point could be z f of z. Then our secant line would have slope f of z minus f of x divided by z minus x. And then our tangent line would have, what would we need to do to get the tangent line is we'd need to let z move across the x-axis and get closer to x. We would have the limit as z approaches x would give us the tangent line. And here is another way to write the derivative. We're going to rely on this first version, the limit as h goes to 0, because it tends to make our lives a little bit easier algebraically. Okay. Let's put this into practice once and then think about when derivatives might not exist, and then you can try to put it into practice on the activity. So let's find f prime of x for f of x is the square root of x plus 1. All right, let's take this one step at a time. So f prime of x, we just decided, is the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Okay, and so that is the limit as h approaches 0. F of x plus h is the square root of x plus h plus 1. F of x is just the square root of x plus 1, and that's all being divided by h. Okay, this looks like one of those situations where we will have to multiply by 1 because we have those square roots in the numerator, and so let's do that. Let's multiply by 1 in this form. Square root of x plus h plus 1 plus the square root of x plus 1 over the square root of x plus h plus 1 plus the square root of x plus 1. Okay, so no algebra to do in the denominator here. And I will, as a forewarning, whenever you're doing this or evaluating limits like this, wait as long as you possibly can to ever do any algebra in the denominator. Usually it won't be necessary. Okay, so now if we multiply in the numerator, we multiply the first two terms and we just get an x plus h plus 1. We changed the sign here to plus because that means the middle two terms will cancel and we're left with minus and x plus 1. Okay, that's not so bad, because this then is the limit as h goes to 0. Let's see what happens in the numerator. We get an x minus an x, a 1 minus a 1. It looks like we're left with an h. Let's see if we can illustrate this without writing it all out again. This and this go away because of this negative. This and this go away because of the negative. This h is the only thing that's left then in the numerator, and then so it will cancel with this h, leaving a 1 in the numerator. So this is the limit as h goes to 0 of 1, we'll stick with red, over the square root of x plus h plus 1 plus the square root of x plus 1. Okay, so again, that numerator simplifies to h. The h in the numerator cancels with the h in the denominator, leaving a 1 in the numerator. And now we're at a place where we can take the limit as h approaches 0. Let's go back to blue. And when we do that, well, there's no h's in the numerator, so it's not changing. As h approaches 0 here, that term is just left as a square root of x plus 1. And as h approaches 0 here, there's no h's, so nothing's changing. So that is also a square root of x plus 1. And that then is 1 divided by 2 times the square root of x plus 1. So what did we just show? We showed that for f of x equals the square root of x plus 1, f prime of x equals 1 over 2 times the square root of x plus 1. Okay, so then I guess we could ask another question. Where does the derivative of the function square root of x plus 1 exists? Another way to ask that question is, what is the domain of f prime of x? So in this case, the domain of f prime of x is, let's see, it can take on 0, it could not take on -1, it can take on 1, 2, 3, so it looks like it's open interval -1 to infinity. So what does that mean? Here is f of x. It looks like the square root function shifted over. It's 0 at -1, and it's growing something like this. Its derivative exists everywhere except at the endpoint here, -1, because the -1 is not in the domain of f prime. And I guess that makes sense, right? How would you draw a tangent line at that point? I wouldn't know what direction to draw that tangent line in, so it seems to make sense that the derivative is not defined there at -1. Okay, let's see, one other thing. We're going to ask when else might a derivative not exist, but first, just a little notation heads up. This idea of derivative is notated lots of different ways. All of these notations are equivalent. They all mean exactly the same thing. F prime of x, y prime, the derivative of y with respect to the variable x, the derivative of f with respect to the variable x, and the derivative with respect to x of f of x. So there's 5 different ways to write the same idea. I'll try to stick with f prime of x dy dx as the two notations that I use most often. When we start thinking about implicit differentiation down the road, we may rely on y prime. Okay, so when will the derivative of a function not exist? Another way to ask that question might be to ask when can we not draw a tangent line, or when does a tangent line not have a slope? Okay, so first, if we had a jump discontinuity in our graph, I certainly wouldn't know how to draw a tangent line at that point. And in fact, if we had a removable discontinuity or a infinite discontinuity, the same thing would happen. So any discontinuity. Also, if I have a picture that looks like this function comes to a cusp or a point, the derivative doesn't exist here. F prime of 0 does not exist. So at a cusp, this looks like a function, something like absolute value of x. And the last place where a derivative might not exist would be if a function has a vertical tangent line. Vertical lines have undefined slope, and so a vertical tangent line can exist. Here's an example, and this example would be something like the function f of x equals x to the 1/3. Generally, we can ask when a function's derivative exists by taking the derivative and looking at the domain of that derivative. So in our example, the domain did not include -1. Okay, see if you can use that limit definition of the generalized derivative to work on the section 2.2 activity and homework.